welcome everyone on the call. I will be talking today about using the pillar diagram in modeling new and emerging CAV features. This is a project that was funded by the Federal Highway Administration. We just wrapped it up, and I would like to acknowledge my team members, David Hale from Lidus, Ali Reza Talibur from he's in Illinois now, and my PhD student, Awad Abdel Halim. So the idea here is I'm going to take a step back a little bit and talk about how you need to approach modeling and simulation of connected automated vehicles. And then I will go in and give an example about how we did that in Vissim. But there are certain facts and certain aspects that we need to be aware of before we delve right into this. The first thing is that there is no single analysis, modeling, and simulation tool that can address connected automated vehicles related questions right off the bat. You usually are going to have to do some extra modeling steps and extra simulation and sometimes development steps. So additional programming is often needed and can be challenging. So it's very important to step back, as I said, and think about all the elements that you need to implement before you go into them. And then scarce and valuable data are needed for design, calibration, and analysis of CAVs. Now, sometimes that data has been used already by the simulation developer in developing some agents that you can use, as we will see later on, but sometimes you need to do it yourself. The general idea is, first, you need to clearly define the scope and the research questions before embarking on the analysis. And you need to consider all transportation system components relevant to the CAVs before defining the project tasks. And then consider the in-house capability and understand, commit to the necessary level of effort. Because usually CAVs, modeling CAVs is a hot topic. So people getting into this, especially juniors and grad students and so on, they might be tempted to try to do everything. But we have to remind them that you really need to do the analysis to answer the specific questions you have on the table, and not beyond that. Otherwise, it will take too much time and too much effort to do it. So the scope that I'm presenting here, the framework, is you define the scope first. So clearly define the questions, determine the list of needs and requirements to answer those questions, and rank and prioritize the list. That's the first step. And then what we are presenting today, what is new, is the pillar diagram. And the idea with the pillar diagram is it's a way to brainstorm and to communicate and to be transparent about what you are doing and what you are not doing related to the effort on this simulation. And I'll talk about that in detail. But the idea is, again, you need to connect the dots on the enable CAV pillar diagram, considering the available tool that you're going to be using, and considering the level of customization that you're going to need to do to that tool to be able to achieve your objectives, to answer those questions, and then brainstorm all the connected components on the pillar diagram. As you can see now in the framework, the first two steps did not even touch the simulation yet. And again, I just want to emphasize that this is a very important and critical thing to do before you jump in and start simulation. Then you define and evaluate your tasks, determine whether the analysis can be done in-house, weigh the number of questions that can be answered versus the required level of effort, and anticipated fidelity of the model. So sometimes you can answer the question with macroscopic modeling, or you can do a mesoscopic modeling, or you can go all the way to microscopic modeling in Vissim and so on. So it's important to know what level of fidelity you are using to be able to answer those questions. And don't forget the data. So I put some questions here, like was the CAV data used in AMS agent development? Are their data to calibrate the model? Is there data to validate the model? So calibration, validation are very important as well. So here is the pillar diagram, and it takes a while to get used to, but I'm going to go through it in details, and then I'll show you some examples before we show the actual simulation that we have done. And the idea here is, again, to facilitate the brainstorming process. In a way, this is analogous to using unified modeling language or system modeling language, SysML, to be able to expose what you're doing and what you're not doing. So what you see in front of you is that you have three pillars. These are the components. And each one of those pillars is specific to a different component. So the first one on the left, as you can see on the top, there is a single vehicle. The second pillar has to do with the multiple vehicles, so it has to do with the interaction among vehicles. And the third pillar, the last one on the right, to the right, is the infrastructure component. Then within each one of those pillars, there are two analysis levels. And then there is another one on top that has to do with the way you look at your data and you look at your model. So basically, you have microscopic and you have macroscopic. And of course, mesoscopic is somewhere in between. And that would be combining certain microscopic element with certain macroscopic element. So that's why I didn't put it here. So let's take one pillar at a time. Let's look at the single vehicle, for example. On the very top, you have activity-based models. And then below that, you have origin destination analysis. So this level in itself speaks to whether you need to look at the activity of the people in your simulation, the agents in your simulation, and you need to look at the origin destination as an aggregate measure instead of individual person that you are simulating. In the microscopic and macroscopic level, in each one of them, you have sensing, you have estimation, you have prediction, and you have control. So whenever we are looking at a specific problem, we're going to look at whether we need to simulate the sensing component. So if you are looking at automated vehicle, for example, and you want to look at the level of are you going to, what's the impact of using LiDAR versus radar versus, the different algorithms used for object detection and tracking and so on, then you need to look at the sensing component. But if you are only looking at the state variables, and the state variables here being the speed of the vehicle, the steering, and so on, just the state variables, not at the sensing level, then that's the estimation component. If you are trying to predict what is going to happen in the next few time steps so that you can make some control actions, then that's the prediction component. And if you want to control the vehicle, and of course we do in terms of simulated vehicles in Vissim, then that's the control component. In the single vehicle pillar, there is no macroscopic part because by definition it's a single vehicle, so you're looking at it in a microscopic level. But in the multiple vehicle, you have everything that I've just said, but you are also having these sensing, estimation, prediction control at the macroscopic level too. And I will show you the example that later is using estimation at the macroscopic level, not the microscopic level. And then you have the infrastructure, and in that, if you are dealing with traffic signals, for example, of course, you don't have activity-based models, and you don't have origin destination in terms of infrastructure, but you have the micro and macro. And then let's not forget the top and the bottom of the pillar. And those are, on the very top, you have the data. And these are with a point and trajectory. So point would be data that you're getting from detectors. Trajectory data will be data that you're getting through GPS or through any communication from the connected vehicle itself. And then at the very bottom, you have the output collection and visualization. And of course, you're not going to be doing simulation if you're not getting the data and using the data. Now, that being described, I would like you to look now at every individual line within the pillar itself, any pillar. Let's take the first one as a single vehicle. You will see that I have 4 columns in it within the pillar itself with different coloring. And these are references to the level of simulation or modeling that you have within that pillar itself. There are certain things that you can do with standard features. So Vissim, for example, is going to come in with some CAV agents already in the newer versions of it. And those CAV agents are going to allow you to do certain things. You're going to simulate certain features. So if those certain features are what you are interested in, then you can do that with a standard feature. You don't need to develop anything beyond that. But it also comes with scripting and with API, application programming interface, that would allow you to go beyond the standard features. So sometimes, you can use a simulation model, but you know that you're going to be doing some programming to be able to achieve what you want. And then there are research tools. These are the tools that you can use to augment what you are doing with a simulation package to achieve your goal. So, for example, if you were to do machine learning prediction, then you are going to use the API or the scripting, but also you're going to collect that maybe to TensorFlow or PyTorch or some other tool outside. And then there is a development level, and these are things that you're going to do yourself, all from the from scratch if you want to be able to answer those questions. So it's very important to know what exactly you will need to do to answer the question. And I keep repeating to answer the question because I want to emphasize that. It's very important to keep your eyes on the prize and why you are doing what you're doing, what question you want to achieve. So even though I focus on the pillar diagram, and I basically already described what is listed here. Even though I focus on the pillar diagram, I want to remind everyone that the pillar diagram itself is one of the steps that the framework includes. So the framework is not the pillar diagram. The framework uses the pillar diagram, but it is very important to understand the pillar diagram to be able to use the framework. And then you could think of the pillar diagram as a game board, like a chess, on which appropriate playing pieces should be placed and connected where appropriate. And why would you do that? Because the brainstorming process that the agency personnel will be involved in will initially target the identifying the piece, placing the piece, connecting the pieces, so that there is brainstorming already done to know and understand exactly whether that is going to answer the questions you have or not. So sometimes, if you look at everything that is needed to answer those questions and find out that they are going to be too time consuming or too much effort, then the agency can scale back. The client might scale back on what needs to be done within the time and budget. So let's give some examples here. And this is the first example I'm giving is a hypothetical example. And I'll give you some choices about what the agents could choose within those examples. And then I'm going to give you a numerical example that we have done using Vissim within this framework. So in this particular example, you could think of it as an agency has a question related to changes in travelers' activities. If some travelers were to be provided with the option or have the capability to buy CAV. So then what you do, you're looking at the pillar diagram, having that question in mind. And obviously, if you are looking at travelers' activity and changing their activity, then we are looking at the activity-based modeling aspect. Now, the question is, I have a piece that I'm going to have to place here, but is it going to be on this part, or this part, or this part, or that part, right? Where do we put that? And here comes the need to know the capability of the software you are using. So if for this example, if you want to do it in Visum, then you're going to end up using Visum with the standard features to achieve your objectives, because you can do activity-based models in Visum in the standard feature. And then the next step would be, I'm going to have to do something here about control, because this is, the person is given the choice to use a connected automated vehicle, and they're going to change their activities based on that. They are going to change that based on the control ability of that vehicle. Otherwise, why they are not using just a normal vehicle? So it might be some features that we need to model there in terms of control. And then again, you go through placing the piece. Is it a standard feature? Is it a scripting and API? Is it a research tool? Or is it a total complete development that you're going to do yourself? And I'm going to go ahead here and put it in the scripting and API, assuming that if you are given a new feature and that feature has not been already put there in the simulation package, but you can do it through API, then that's a level of development that involves. And then you're going to connect the dots. So the convention I'm using here is, if it's a straight line, that means the software has the ability to have that communication happening already by default within the standard feature. If it's a dash or dotted line, then that means you're going to have to build it yourself. So meaning that you're going to have to script something or process the data and so on. So when you see a dash line over here between the data and the ABM, that just means you're going to do some analysis before you use your data into the software. And then I have that connection as well in the dash line between the control and the output, and that means you're going to do that as well. You're going to do that scripting to collect the data, because it's something that you put yourself, certain features you put in self, but maybe you are getting some data about how those vehicles are controlled inside the simulation. So now let's say we have done that, and you had a team, and the team met in a room and brainstormed and got that done. The usefulness of the pillar diagram is that if somebody comes into the room to join the discussion, they already know what you have discussed. They already know what you think about which elements of simulation you need to do and at what level as well. So somebody might come in and say that, but where I wanna be able to predict also what the users are gonna do for the next day when they make the decision today. Then maybe you need to add a prediction component, and if it is not in the standard feature, maybe you're gonna have to put it here in the API. So people know exactly what the project is going to be doing and what it is not going to be doing, and that's a key point. So some questions related to what I've just put in there. Why does the analysis not involve pieces related to the multi-vehicle or the infrastructure pillars? And the answer is because the question raised by the agency does not involve the interaction between CAVs on the network, nor does it involve the interaction of CAVs with the signal operation. Does that mean the CAVs would not interact on the network or not go through traffic signals? Not at all. But the question raised by the agency does not involve that level of analysis. So we do not want to measure with the micrometer while cutting with an axe. And I'm going a little bit slow on the first part of the presentation because I want to emphasize those key things. Is that you have to always keep in mind what's the question that you need to answer, and don't go beyond that when you're doing the model. So here are the analysis steps. Here is the framework. You're going to list the question that need to be answered. You're going to identify where the needs are in the pillar diagram, considering the available tool. In this case, what we're using later is Vissim. Then determine the required extra steps and tasks to enable the AMS tool to conduct the analysis. And then brainstorm and iterate step 1 through 3. So don't go to the next steps until you have everything over here with consensus, so that you know what available resources and what additional resources you need. After that, complete the enabling tasks and then perform the analysis. Then answer the question. You have to remember to go back, loop back to answer the question. That's why you had them. And then provide the information on how to do that safe deployment and operation, and then make informed decisions for infrastructure investment based on these steps. So if you're analyzing several strategies, then you can look at those outcomes and make the decision at that point. So here is a case study. EcoDrive with transit signal priority. The scope, the impact of the CAV operation when you have a smart transit signal priority application. So that is going to need you're going to need to do transit signal priority. You need vehicle to infrastructure communication. You need vehicle to vehicle. You need the autonomous vehicles themselves to be able to simulate those, and you need to simulate equipped buses. The questions, and this is of course a hypothetical example, but keep that in mind, how we're going to modify those questions later on. So imagine that your client is coming in and say, these are the questions I have. What is the impact of the CAV eco-driving operation when I have already TSP strategies at the signalized intersection? And what is the impact of the CAV penetration rate on the overall system today? And what is the impact of the application on bus punching? Then, okay, you need to define your requirements. I need to be able to simulate CAV eco-driving operation. I need to be able to simulate CAV interaction with mixed traffic, because there is going to be some blocking and slowing down and lane changing in response to that CAV movement. I need to be able to simulate the CAV vehicle to infrastructure operation, because that CAV needs to know when the time is going to change to green. What is the time to green? So it can slow down and speed up, choose a trajectory, an optimized trajectory to arrive at the signal just as the queues are clearing. So that information needs to be communicated to the CAV as it implements that eco-driving. And eco-driving, for those who are not familiar with it, is just the ability of the vehicle to use the information from the signal about when it is going to start the green. So if the signal now is red, you don't want the vehicle to, or even if it's green, but it's about to turn red, you don't want the vehicle to be ignorant of that signal timing and continue with the same speed only to arrive and stop and then start up again. You want it to optimize its trajectory so that it arrives at the signal just in time to move forward after the queues have cleared. I'm defining that loosely, of course, but I guess you get the idea. And then I need to be able to simulate the transit priority algorithms at signalized intersection. And the data, of course, traffic volume data, signal timing plans, the detector locations, and the bus schedules, and then encapsulated data so that we don't forget. Data is not necessarily just the raw data that is given to you. If the developer of the simulation has already encapsulated the data in agent behavior, like Vissim has done with CAV from the coexist project, then that's something that you need to account for as well, to be aware of it. So CAV eco-driving, the buses and the traffic, so even how traffic moves, this is in a sense coming from the Whitman model and then you can calibrate it. But the fact that it has been developed based on data encapsulates that data. And then you have the signal TSP operation. So what are the components? Now think about the pillar diagram and having that brainstorming with your team before you move on and you actually do the task themselves. So the components in terms of the single vehicle pillar, I'm going to need a microscopic component because I need the location and the speed of the CAVs and buses. So I need them at a microscopic level. In terms of multiple vehicles, I need them at a macroscopic level because I need the Q lengths at the signalized intersection to be able to inform my CAV to do the eco drive. And I need the flow on the link. The infrastructure at a microscopic level because I need the signal state, the time to bloom, and the detector status in my simulation. And then connecting dots, I need the communication between the CAVs, the buses, and the signal. So it looks like this in terms of that pillar diagram. If you look at the single vehicle, I am putting in the control at the microscopic level because I need to be able to adjust the behavior, the control behavior of the CAVs to do the eco drive. And I'm putting it at the scripting API column. And that's because, yes, you can use Vissim to put CAVs, but they are going to just drive normally within the traffic with the CAV parameters, of course. But they are not going to do eco driving with the signal. So we need to use API to do that. And then at the multiple vehicle, I need the control. So those CAVs need to be able to drive differently from the normal traffic, but I need it at the standard feature level because in this case I'm using Vissim. That was Vissim 11 at the time, and even in Vissim 2020 or 2021, you have those CAV agents in there. So if you just want to simulate how those CAVs are moving and the control aspect of it, you can use that with the standard feature. And then I need the estimation at the macroscopic because I need the Qs. And Vissim can give me the Qs within their standard feature. So I'm putting that circle here on the standard feature. And then at the infrastructure, I need control, and I need that at a microscopic level. And I can do it with the RBC controller because RBC controller in Vissim can do transit signal priority. So I don't need to develop something new. I can use what exists. And then I'm connecting the dots. So yes, of course, the data, I need to connect that with the control and estimation, and I'm going to get some output in the output collection and visualization part. Whatever I'm controlling in terms of single vehicle, I'm going to need to extract that data, and I can do it using the standard features in Vissim. And then also for the infrastructure for the signal operation, I need to get the data out. I'm having this solid line here between the Q lengths and the controller because I'm going to need the Q lengths to use in my controller. And I'm connecting this with a dash line between the single vehicle CAV doing the eco drive with the traffic controllers because we need to do that in scripting to get that information. So again, just to emphasize this before I move on and go quickly through the simulation itself, it is important to do it with the pillar diagram because, again, if I show this to somebody, they can immediately see that there are certain things that I'm not connecting and that I don't have any circles in them. And because what I've done here is enough to answer the questions I've put there. But if they want to add an additional question, then they know and they can have a discussion with me about where more do I need to put circles and connect them and what is going to be needed to do that, to achieve that. So you're giving that pillar diagram to 3 agencies, hypothetical agencies, and what they're doing here is agency 1 is saying that, okay, great, I'm going to do this pillar diagram as is, So they accept the task and implement them. This is going to require Python programming for the microscopic control of each CAV. The rest of the tasks are implemented using the standard AMS features. So they only require familiarity with the tool. The rest of the document in terms of the report, but the rest of the PowerPoint is going to describe how the tasks are implemented and what the resulting findings are. But it's good to mention that there are other options, right? So another agency might say, in-house, I don't have the Python programming capability. They only want to use the standard features of the analysis and modeling simulation tool that they have, whichever tool that they're using. So they need to reiterate the modeling steps and understand that they can only answer the following questions. If they're not going to do that programming, if they're not moving that CAV in the microscopic controller to the API part, the scripting part, then they can answer the question after striking out the echo driving component part of it. So what is the impact of CAV operation with TSP strategies at the signalized intersection? But they have to understand they're not doing echo driving anymore. And if that's okay with them, that's fine. If not, then they know that they need to get somebody, a consultant or something that who would be able to do that API part. What is the impact of CAV penetration is not going to change whether you do that API or not, and what is the impact of the application on the bus punching. I'm putting application in between quotation marks here just to say that your application now is different. It's not what it used to be. Agency C is going to use a similar tool. So they're not going to use Vissim in this example. They want something else. And that other tool, let's say that they do not have an encapsulation of the data in their CAV agents. So that agent decide, they brainstorm, they decide that they want to use that different tool, which is going to mean that they're going to move the microscopic control in the middle pillar from a standard feature to scripting API. But let's say that agents, they are familiar with the Python, they're familiar with programming, they don't have a problem with that, and they're gonna do this. They're okay with it, so they can do that. So they decide to go with this option. Because they also have access to local CAV testing site data, so they really want to calibrate and develop CAV agent themselves. That's fine. In that case, there's no change to the questions that are needed or required. It is just that there is a difference in the simulation effort that they need to take. So that's the focus on the pillar diagram. Now I just want to go quickly here and close the loop of about how do we finish that example in Vissim and go very quickly on this so I can have time for questions. So this is an example. You will see from a Blacksburg site where you have the buses over here and we have a traffic signal over here, and we want to see if we are implementing transit signal priority with the CAV and whatever that I've described so far. So you can go in Vissim, you can create new vehicle classes, and you have the composition as well created, and then you do those composition consistent with percentage breakdown of different vehicle types, and the new vehicle composition is going to be the new type CAV, and then you go ahead with assigning those vehicle compositions to the vehicle input. In our case, we use two vehicle inputs on links 2 and 4 that are the northbound and southbound direction of Main Street. But what I've done here, just to do this quickly in one simulation run, is change the CAV percentage in one of those inputs in the northbound. What is the southbound? We'll see when we look at the results. But one of those approaches has CAV percentage changing in time, increasing over time. So you start with like 0% and you go all the way to 100%. That, of course, is not realistic. It's not going to happen in that sense, but I wanted to see it in one simulation shot. The best way to do it, if you want to do this very comprehensively, is to run multiple Vissim files, one for each scenario. and then you plot it. The only reason I did it this way is I wanted to do it quickly, and I want to see it in the same graph to see whether it is worth investigating further or not. So anyway, in this simulation, we had 15-minute warm-up time, and then 2 hours of simulation, and some time at the end to clear the system. So you create the CAVs, you assign their behavior. There are 3 CAV behaviors in Vissim. From the coexist project, you have AV cautious, normal, and aggressive. This is a normal. And then we did the urban driving behavior, and we assigned the normal behavior. As I just said, I was getting ahead of myself. And then, of course, Vissim has additional features that you can include. So you can create custom functions, acceleration and deceleration if you want to, and so on. Then what we did here is use a user-defined attributes to carry out the new task not readily available in Vissim. Defining the attributes, assigning them to Vissim object is a much more efficient way to carry out repetitive tasks. And then here we define attributes and assign them to all vehicles in the network that actively calculate the distance to the nearest signal head. So the idea is, as vehicles are moving in the network, they are collecting the signal information from the nearest signal head, but we have an attribute for every vehicle that whether it's a CAV or not, if it's a CAV, then it can use that information. If it's not a CAV, it will ignore it. So that's one simplifying way to do it in that. And then we are calculating the distance to the signal head, and we are changing in every simulation time for only the CAVs an optimal trajectory to reach the signal. And so now we have CAVs in the network with distinct driving behavior and attributes that allow communication with the signal. You can create more attributes. The idea is, Vissim is very flexible in that sense, and you can develop any algorithms if you're using the scripting and you're using the API. In this case, we're using scripting, obviously. Then we created a Python script with the change speed function that is run at the end of every simulation time step. So you can get that trajectory implemented. And as I said, we did it in one file in this case because I want to show how they're getting the standard results from Vissim in figures here. So I'm looking at the vehicle travel time measurements. And it is, yes, the main street north, the northbound is the one that has an increasing percentage of CAVs. The southbound is the one that I set up to have 100% CAVs. And the Alumni Mall is the side street that has normal traffic in it. So I just wanted to relate it visually to folks who are looking at the results, what's the impact of the CAV. So obviously when you have all CAVs, you have low average delay. When you have mixed CAVs traffic, you have higher delays, but not as much as the delay that you have for the normal traffic. And this is time interval simulation on the x-axis and delay on the y-axis. And then I have 3 different lines here. The bottom line is how the CAV delays changes during the simulation, and it's not much. It is the lowest of the normal traffic and the buses. But you can see that the normal traffic, it has way more delay than the CAVs, and it is increasing as the simulation is running. And the idea is because, again, on the northbound, I had the increased percentage of CAVs. So actually having CAVs in there, it is going to increase the traffic delay for the other vehicles, not the CAVs. On the buses, it's a little bit weird here, up and down, but the reason is when I looked at the animation is that sometimes you have 2 buses arriving during the same cycle and causing the transit signal priority to take more green than usual. And sometimes if you get 2 or more buses, I think I had one case with 3 buses in a cycle. They could not fit within the window anyway, so they had to experience a lot of delay. So all in all, the buses delay were more than the normal traffic and the CAVs. And then I had the bus travel time all the way to their last station, and I looked at the standard deviation to see if there is bus bunching happening, but they weren't changing. There was no change in the standard deviation of travel time. So looping back and answering the question, what's the impact of CAV eco-driving operation in TSP strategies at the signalized intersection? CAVs will experience much less delay than normal traffic, but normal traffic delays will increase. What is the impact of CAV penetration rate on the overall system delay? The increase in penetration rate will increase normal vehicle delay. It is true, and when you look at it, and when you think about it, or even look at the animation, it is going to increase the vehicle delay. But sometimes we forget that. We think CAVs are going to come in and going to enhance the overall system delay. They're going to enhance their own delay, but they're going to have an impact on the normal traffic, at least at signalized intersections and at least at a single component like that, single intersection. What's the impact of the application on bus bunching? There was no significant impact on bus bunching. So I just showed you an example, but I wanted to loop back all the way and remind you that you start with the questions, you're doing all the work to be able to answer those questions. So you need to loop back to them and answer them. So in a summary, the proposed framework shows the application of the pillar diagram to understand what the agency is and is not committing to do. And I'm going to say is not committing to do is very important to show. And there are 9 steps to complete the analysis. And then the case studies that showed you the eco-driving case to illustrate single vehicle, multiple vehicle, and infrastructure control applications and signalized arterial application. Conclusion, conducting detailed microscopic analysis of CAVs will require using simulation tools with API and or scripting tools. The analyst must consider the overall transportation system operation with its interacting component in tandem with the question they are trying to address. So again, as a reminder to especially the junior engineers and grad students, sometimes you do something in an individual vehicle, but it's going to have an impact on the overall system. And you just need that pillar diagram in front of you to brainstorm and think and put everything in context to know what else needs to be simulated. And then there is a trade-off between conducting detailed microscopic analysis if you need to make high degree of assumptions versus conducting a higher level mesoscopic or macroscopic analysis in the absence of rich data sets. So if you don't have the data sets, sometimes you might not want to make a lot of assumptions and insist on doing that simulation at the microscopic, you can do it at the mesoscopic, if that will give you, require you to do less assumptions. That is the end of my presentations. As I said, this was a project funded by FHWA through Saxton Lab and Leidos, and these are my contacts with the FHWA who oversaw this project, and I'm thanking them and thanking Leidos for their support. Thank you very much.